Welcome! In previous clips, we have shown how water can be stored in two types of aquifers, unconfined and confined. In this video, we focus on the first type. Unconfined aquifers develop when the uppermost part of the Earth's subsurface is formed by permeable rocks. Water from precipitations infiltrates the ground, is blocked by an impermeable layer, and starts saturating the permeable medium. At the same time, water will start flowing downwards towards the discharge domain, establishing a steady-state situation. As a result, the upper boundary of the saturated layer, called the water table, lies within the permeable medium itself. This is different from confined aquifers. From the drawing, you can also see that the unconfined aquifers are in direct contact with the surface of the Earth, with all the activities which take place there. In the schematic cartoon, you can see in more detail the main elements of an unconfined aquifer. You see the permeable upper layer, loose sediments or rock, underlain by permeable lithologies. With the onset of precipitations, you see the water flowing downward and laterally, and the resulting water table situated in the permeable layer. Note that in the scheme shown in the slide, the water table intersects the topography at the level of the river, which means that the water will flow from the aquifer into the river. The river is a discharge zone. Quantifying and managing water resources stored in the unconfined aquifers is only possible if a correct map of the water table is done. To construct such a map, piezometric wells are typically drilled in the area of interest and positioned on the topographic map. From these wells, the height of the water level with respect to a reference level is measured and plotted on the map. Eventually, contours are drawn to interpolate between the data points. Let us look at a somewhat more realistic water table map. Here, you see the topography of the area. Along the section AB, to the right of the map, you see the topographic profile we will look at. A number of wells have been drilled in the area, and the position of the water table with respect to the reference level has been determined. Eventually, contour lines are drawn. Projection the position of the water table along the AB section on the altitude plot, you see clearly that the water table is not flat and is generally higher in correspondence of the relief rather than in the depressions. The water table intersects the surface at the river floor and in correspondence with the small lake on the right-hand side of the profile. We conclude that these water bodies are partly fed by the unconfined aquifer. With this kind of maps, you will be able to predict the position of the water table in other localities of the map, for instance, where people want to build a house. The position and topography of the water table will remain constant as long as the geometric and physical properties of the subsurface remain constant and, more importantly, as long as the recharge and discharge also remain the same. If this is not the case, then very important modifications affect the system. Imagine, for instance, a situation where precipitation increases significantly. This will lead to a rise in the water table, and areas which were previously just above it will be flooded. In times of decreased precipitation or increased extraction, the water table will descend. This has a number of consequences. For instance, deeper wells will need to be made, and water bodies, such as rivers, which act as discharge areas, will start charging the aquifer, with water moving from the river to the aquifer itself. A third related consequence is land subsidence. Water removal will allow further compaction of non-lithified sediments, resulting in subsidence at the surface of the Earth. The engineers building the Leaning Tower of Pisa were apparently not aware of the consequences of extraction of water for the city. I'd like to conclude this clip with a great example of how people thousands of years ago had understood unconfined aquifers and figured out how to use the non-horizontal position of the water table. People in many countries, such as Iran, had realized already that the water table had a slope and was higher towards the recharge areas in the mountains than in the low domains. They started then digging horizontal tunnels from the flank of the mount to the interior of the mountain, of the hill. Once they hit the inclined water table, water started flowing, bringing life to the previously dry region, allowing human settlements and agriculture. The underground tunnels were then equipped with vertical shafts and other infrastructures. These systems are called catheters. In some places of Morocco, there are tens of these tunnels feeding communities and their activities.